Welcome to session 8 of Electrodynamics 2020. So I hope you're coping well after this strange week that we've just had, which was meant to be exams, but at least on our side didn't really happen. We're now entering the kind of second half of the course. We've done all the static things with electrostatics, magnetostatics, in vacuum, and also in matter. The second half of the course is really going to focus on dynamical effects. The plan for today is really to do the beginnings of electrodynamics and actually to get to Maxwell's equation. So the objectives, essentially, we're going to talk about Faraday's law of induction, which is really the founding block for everything dynamical here. Just going to give you a few words about the electromotive force, how you should think about that. Lenz's law is a trivial little thing that you might already know, but you'll relearn soon. We'll do some practical applications, parallels between Ampere's law, Faraday's law. We'll discuss the concept of inductance. We're going to talk about the energy stored in magnetic fields. We're going to talk about what James Clerk Maxwell added to the theory of electromagnetism, essentially how he completed the set of equations into a coherent whole that's known today as Maxwell's equation. So we'll discuss the displacement current, and then we'll give the final form of Maxwell's equations in vacuum. Okay, so that's the plan for today. We'll just see how we do. Okay, so let's just shift to our electronic board. So electrodynamics, well, what do we want to start with? We want to start with work of some really nice researcher. I don't know if you know much about Michael Faraday, but it's really worth having a look at his biography, because it's quite interesting. Yeah, okay, so Michael Faraday. So dates 1791, 1867, you know, big historical dates, yeah, 1791, the core of the French Revolution, 1867, Canadian Confederation, yeah, anyway, so non-related to Faraday's life. Faraday was essentially a genius experimenter with all sorts of different things. He worked quite a lot in physics, a bit in chemistry as well, and possibly his most important observations, at least as far as we are concerned, they were made in the year 1831. So he did a number of experiments. Actually, in Griffiths, you have some statements about what happened historically. I think some violence was done to actual historical events. So I'll just present it slightly differently. So what was the simplest, or at least the first really important thing Faraday did about induction in 1831? So it's quite straightforward. So imagine that you have metal ring. Okay, again with my drawing skills, you'll see it just looks like a real metal ring. So just, use iron, for example, so you can get some good magnetism in there if you put some coils around it. So the idea is that you would wrap, or Faraday wrapped a coil around one side, like this, okay, and connected this coil to a little battery. Okay, that meant that some current was circulating in there, and it created some magnetic field that was then transmitted through the ring. But what he also did is that he just wound another coil onto the ring like this, okay, and connected that one to a galvanometer. That's something to measure current. And what he noticed, what he observed, is that when the current in loop 1 changed, there was a current observed in 2. 2 being, this coil here. Okay, so that's the fundamental observation that triggered Faraday into studying these things in much more detail. So it's quite a simple setup, if you want. It was a very clear observation. Actually, you might know also about Ørsted's observations that if he, earlier than that, I think it was in the 1820s, Ørsted did a different thing. He had just a compass needle, and then he had an electrical circuit around it, and if you put some current in the circuit, he noticed that the compass needle would change. So then it's, if you want, a building block of Faraday's experiment, because what Ørsted observed is that an electrical current generated a magnetic field. What Faraday now sees is that the magnetic field created by the current changing in here actually creates an electric field in the second circuit. Okay? So there are lots of other experiments that Faraday did also in the year 1831, really a very large number of them. They're all based on the idea of a time-dependent magnetic field. So you could have, for example, just say another battery here, and then you've got a loop like this. So this creates a field, and then you get another loop plugged onto our, oh sorry, that was a very square loop. Let's do that again. So you've got another loop that you connect onto your galvanometer, and then if you move this loop here, while there's a fixed current circulating through it, you would also see some current looping through this loop here. So another one, another thing you can do is just again take your galvanometer like this, and you've got your nice loop, and then you take a chunk of material which is magnetic, and you just like move it as fast as you can through the loop or in the vicinity of the loop, and again you would observe a current here. But that's the central observation of Faraday, right? So his statement is that if you have a time-varying magnetic field, okay, induces an electric field. Yeah, so that's the interpretation that Faraday made. He interpreted the current appearing in the subsidiary loop as being the result of some electric field which was acting along the loop in there, therefore moving charge, therefore creating a current. Okay? So the way to define this or to talk about this in more detail uses a little concept that we're just going to introduce now. Okay, so to quantify this, we will use the concept of the electromotive force. Okay. So electromotive force. Okay, in some references, different books, you might come across a different term, which is electromotance. In a sense, I think electromotance is a technically better term, because the electromotive force, ironically, is not an actual force, and it doesn't really necessarily lead to visible motion. But anyway, so this is very often used in the literature. It's very often abbreviated as EMF. So if people say, oh, you just measure the EMF, blah, 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 that's what we're talking about. So what is it? It's quite simply defined as the integral along a closed path of the electric field, okay, dotted it to the displacement. So you can think of the EMF in a number of different ways. If you want, if you have a certain loop like this, and you take a unit charge and you move it around the circuit, okay, it's the energy that you accumulate as you do that. You could also interpret it by thinking of, just doing an imaginary cut on the on the wire and measuring the voltage difference between the two. Okay, so maybe a better analogy to first understand this is, imagine that you've got like some water pipes. Okay, so I've got this, and imagine that it's a little tube, yeah, that contains some incompressible fluid like water. Okay, the way you should think about the electromotive force, it's, if you want, the force per unit mass that you would have inside this. If you want, you kind of almost think of it as the current you have here. Because the fluid is incompressible, if you push on the thing here, then the whole fluid is going to want to move and circulate in a certain direction. So the analogy is quite close, if you want, to that of an incompressible fluid. For example, if you have a battery, the voltage difference that's induced by the battery is really the kind of equivalent of the electromotive force that you have in there. So the statement of Faraday. So Faraday's law, what it says is that the electromotive force around a circuit is, we just wrote this, right? So E dl. What is this? It's the negative of the change of the magnetic flux through the surface defined by the path as a function of time. Okay? So, if you want, so for, let's make it for a stationary loop. Okay, what it tells you is just that the integral over the path of E dot dl is equal to just minus the integral over the surface defined by the loop of the time derivative of the magnetic field. Okay, dotted into the surface element. Okay, so one of the things you have to understand is that the path that we have here doesn't have to be like an electrical cable or anything like that. It's actually any imaginary path that you can think of. You just draw a loop in space, and that is going to be true. Okay, so since it's true, for any path, what we can do is just use Stokes' theorem to rewrite this integral over the loop as an integral over the surface of now the curl of E, okay, dotted into dA. So what we get now is Faraday's law. Faraday's law in now differential form. Okay, which now tells us that the curl of E, okay, again, these are all vectors, right? The curl of E is just the time derivative of the magnetic field. Okay, so that's a super fundamental equation that we had, and it of course complements our electrostatics equation that we had. You remember in electrostatics we had that the curl of E was equal to 0, but that's of course because in electrostatics and in magnetostatics the time derivative of the fields just identically vanish. Okay, so so that makes it quite well connected to what we've seen up to now. But now you see we've gone dynamical. Time dependence is showing up in our fields, and that will lead to lots of interesting effects. Okay, there's a kind of little trick that that one can use. You remember all the rules for right-hand rules and things like that. There's a little trick to make sure you get all the signs correctly, because you have to orient your surfaces everywhere properly, etc., etc. The trick is really called Lenz's law, and there are many different ways to state it. So in Griffiths, the way he writes it is that nature abhors. Sorry, I'll just rewrite this. Nature abhors a change of flux. Okay, what it means really is that if you were to change the magnetic field in a certain way, so if you have a certain loop like this, and you've got a field coming out of it, and say you increase the field, then the current in the loop will be such that it will try to counterbalance the change that you're trying to impose. Okay, so that's just a kind of trick you can use to make sure that you get the right answers that are given to you. Actually, just a side note here, if you want, this is a consequence of a principle called Le Chatelier's principle. Le Chatelier. So, what does Le Chatelier's principle tell you? Well, if you have, say, a thing in equilibrium, you have a potential like this, that's your equilibrium position. If you try to move away from the equilibrium, okay, then the force that you generate goes against you. It tries to bring you back to equilibrium. Okay, the reason for this is just because you were at equilibrium, the kind of generalized derivative is equal to 0, so when you start moving, you want to go back towards the minimum. So it's the same thing here. You're at an equilibrium situation, you try to change something, so the system resists at trying to bring it back to equilibrium. Okay, so that's the first part of our course for today.